my wonderful AP students. Time for your day 25 video. This is the big one. We're going to introduce topic 4, systems, momentum, and impulse. You're going to take all the major definitions today. You're going to write down how to draw these new pictures of systems, what they mean. And finally, you're going to do 1 and 2 examples that are non-mathematical to make sure you understand how to set things up. Because in this class, as well as life, it ain't always about the math. It's about understanding what the heck is going on here. So topic 4 is linear momentum, and it's got a couple parts. The major idea I'm going to get to you in this topic is that linear momentum in a system is conserved. Okay, so what does that mean? Here's my official kind of definition. The amount of straight line motion between objects is the same before and after they interact in an isolated system. Whew, that's a mouthful. So it doesn't really make much sense. The amount of straight line motion, okay, so the amount of motion, is that velocity? I'm not really sure. But the amount of motion, or just motion movement I have between objects is the same before and after they interact. Okay, so if I'm moving and I push you and you start moving, that means I have to give you some of my motion. All right, okay, that makes sense. So motion does not involve curving, so this will be a big deal in a little bit, is a conserved quantity in an isolated system. Okay, so if there's nothing else interacting with us and you and me are pushing each other, the motion before and after our push has got to be the same overall. So if you and I are not moving before and we push each other, we can both be moving, but someone has to cancel out because we had no motion before we interacted, as long as nothing comes from the outside. So here's where it gets really careful. We now need to define what a system is as well as isolation. You might think isolation is what I do when I try to study, but that's not true here at all. A system is 2 or more objects interacting. You sitting on your chair, you're a system. You screaming at your parents, that's a system. All of us on this wonderful planet, that's a system. The entire universe together is another system. An isolated system means there's no external imbalance of forces. In other words, there can't be a force that is made from something outside the system, and it can't be unbalanced. So if you define a system as you and your chair chilling there, if someone gives you a shove, that's from outside the system. Therefore, momentum is not conserved unless you somehow expand your system definition to include that force or person. So, here's an example. Is this an isolated system? 2 cars collided on a gravel roadway on which frictional forces are very large. Is that an isolated system? Pause, think to yourself. Okay, you're back. We're going to say, no, it's not an isolated system. Your system here is probably going to be the 2 cars hitting each other. But the friction is the external force, and the friction takes away motion from the system. So if both cars start with some motion, that motion between both cars is getting less and less and less combined because it's going to friction. So hey, where does the motion from the cars go? Where does friction deliver the motion to? And the answer is Earth. So if you said the system here was both cars and Earth combined, then we would say, yes, it is isolated. But it's kind of tough to do. You just heard my phone. That's awesome. It's kind of tough to do there because Earth has got so many other things going on. So when 2 cars are colliding with friction, both cars are slowing down, which means somehow the Earth is gaining speed as well, or maybe it's just absorbing the motion. There's all these different things happening. Question. Over the last 200 years, has Earth been an isolated system all itself? Or in other words, has all the motion on Earth stayed on Earth? And vice versa? The answer is, of course, no. First thing is, you have all these kind of meteorites that are hitting, and those are either going to add Earth's motion or take away Earth's motion, depending on which way they hit. If Earth is moving to the right in outer space and something hits left, that's going to take away motion. If Earth's moving right and something hits from the right, it's going to give it motion. And the second thing, which is kind of cool, is that rockets that leave Earth permanently have taken motion from the Earth to do it. So every time we send a rocket to outer space and it never returns, Earth is now permanently slower. So many billions of years, actually a couple billion years from now, when Earth finally stops and gets exploded by the sun, it's now a tiny bit less where it should be because we use its motion to keep on moving rockets. So let's show how to represent it. You're on a skateboard that can roll without friction. Yeah, right. A friend tosses a bowling ball to you. Is it an isolated system? Obviously no. You and the skateboard are probably considered to be the system here. The friend who tosses the ball, well, that friend pushes the ball. I mean, the ball pushes back, so the friend's going to move backwards while the ball moves forwards. Or if the person's running when they toss it, they're going to slow the forward motion. All these different things that can be possible. What matters is, however, is this picture here. The system is something that says circle, and that's you and the board. This arrow shows that something is entering your system, thus giving it momentum and motion. So the momentum is not conserved inside the system because the ball is going to give momentum to the system. My explanation is right here. However, momentum is not conserved in momentum is not conserved in a non-isolated system, but if we include the ball right before it comes in, we can see the momentum of the system and the ball is conserved. The motion of the ball is from outside the system, so the system itself either gain or lose overall motion. Long story short, the ball's moving plus still you and the board, and if you catch it, it's going to end up moving all y'all. So both you, the ball, and the board are going to move. Will you be moving faster or slower than the ball? Obviously less. Slower, because the ball now has to move you, the board, and itself, which means more stuff to move. There's not going to be as much velocity to that motion. And we're starting to see how Newton's laws take place, because that idea of inertia plays a big role here. Okay, so now you have caught the bowling ball. You toss the bowling ball back to the friend. Is it an isolated system? In this case, the answer is kind of yeah, because the system starts off with you, ball, and the board. And the ball is going to move, but it's going to cause you to move as well. So if you include the ball in there, you are isolated and momentum is conserved. The motion of the ball comes from the system, so it is conserved. In other words, the still ball plus still you and the board, when you push the ball forward, there'll be an equal and opposite force backward. So the balls move forward, you're going to go backwards. Combined, the motion equals 0, because that's what it was beforehand. So it's not like we create a motion out of nothing, but at the same time, it's you push the ball forward, you have to go backwards. Which one's going to move more? Well, if the ball is lighter, it's going to move faster than you both. If you both weigh the same, if somehow you and the skateboard combine equal to the big bowling ball, you'll both move at the same velocity. This is kind of the thinking you need to do, and you will be doing with me over the fourth topic. In other words, systems can be defined by you, just like positive and negative of the other things. So you can define what a system is. But to make sure everyone's on the same page, you need to draw these little system drawings to make sure everyone knows what the system is. And what's really neat is that the AP exam for the first time is actually going to include these little circles and the next kind of graphs I'm going to teach you in, I believe, a day or so. So you're going to get really used to this because this is what you're going to be seeing. Now let's write down some definitions. There are two major ideas in this topic, and that is momentum and impulse. So here's my table. Notice idea, words, equations, units, how it's used. I want you to pause the video, write all this down very nicely, or you could just listen to me and then write it down after it. I don't really care. I'm about to assume that you're ready to listen to me in about 5, 4, 3, 2, 1, booyah. Okay, momentum. We're going to use the symbol of P there from, I think, progress or possibly a German word. In other words, momentum is the motion of objects which involves both mass and velocity. It's not how fast you're going, it's how much motion you have. And if you ever try to stop like a really heavy person from running, there's a lot of motion, even though they may not be going very fast. And mathematically, the equation is simple. Momentum is mass times velocity. It is a vector, so it can be either positive or negative. For units, we know mass is in kilograms, and velocity is in meters per second. So momentum is in kilogram meters per second. You might remember that kilogram meters per second squared is a Newton. So momentum is also a Newton times a second, called the Newton seconds. Now, it's used by us in systems where two objects interact. Momentum is usually conserved. This allows us to predict what's going to happen when two objects interact. Either when they hit, they separate, or do all the kind of things. So soon we're going to watch a couple of car crash videos and see how different cars can use the change of momentum to do things. And the idea of change of momentum is our next topic. Next idea. Impulse. Impulse, the symbol, there's two of them. There's delta P, change in momentum, or sometimes I. In other words, impulse is the change of momentum of a single object. Momentum is usually the motion of an object or objects. Impulse is always a single object. You're looking at how much it changed its motion. So there's two equations. The first thing you could do is delta P is the change in momentum. And from the above equation, it's just your final momentum minus your initial momentum. Nothing new there. But if you're really interested, mass times velocity. Well, mass times acceleration is a force, and acceleration is velocity over time. If you just derive it, you end up getting that momentum is also a force times the time. Notice this average force. Because force can change, it's just the overall average force times the time. That's also the change of motion, which makes sense. If you want to change something's motion, you need to have a force on it for some time. The more time you have a force, the bigger the change of motion. The longer you're pushing something, the more it speeds up. Or, if you want to slow something down, the longer it takes to slow something down, the less force you need. It's also measured in the same units because it's just simply a change of momentum. And how it's used. During a change of motion, a force for a certain time causes that change in motion. In order to slow something down or speed something up, you need to change its motion by applying a force for a time. And with that, wonderful students, I believe, we're about to do our last example. I drop a bear, like a teddy bear, and a ball. Both have equal mass on the ground. The bear hits, it comes to rest. The ball hits and rebounds up. Boing. And by the way, there's actually physics on why they sound differently, which is kind of awesome. Here's a weird picture. I tried copy and pasting, but it's kind of an angle, so just crick your head. The bear hits and stops. The ball bounces back up. Probably not the same speed, but definitely bounces up. We're going to see this as a non-isolated system. Why? Well, the bear has motion and then it loses it. What does the motion get transferred to? The Earth. So the Earth speeds up, and the Earth is not part of this system because the system is right now probably defined as the bear separately and the ball separately. Because you can't really figure out the momentum of the Earth before unless you call it zero. This should read ball, except the picture got in the way. Both have an impulse. Both things change their motion. The bear goes from motion to zero. The ball goes from motion to backwards motion. Which one's got more impulse? My answer is the ball, because the ball has to change its motion from downward motion to zero and then keep changing it to go to an upwards motion. Whereas the bear just has to change its motion from downward motion to zero. Which means they both have a force upwards because the bear slows down and stops. The ball slows down, stops, and gets pushed back up. So normally we think the ball's got more force, but we can't be so sure. If the ball takes a long time to come to a stop and bounce back up, that long time may mean it has a very small force with that larger impulse. If the bear quickly comes to a stop, that smaller impulse can yield a much bigger force. So there's a lot going on in these systems that I'm going to teach you. This is just the beginning. Please come with your questions. We're going to express this both conceptually and mathematically in class. I hope your day is as pleasant as you are. Goodbye.